Alright, hello guys. Apologies for such a late upload for the delay because I've been dealing with personal stuff lately. But this unfortunately is not the video where I go over the past paper and answers to my previous two videos, which if you haven't seen, you should go check out, where I attempt the SPM 2020 AdMats paper 1. Today, I would like to delve into a topic that I've been thinking about recently for some reason, but I just had to make a video about, and it's on progressions. Now, why progressions specifically? Well, because I've been thinking a lot about, studying or restudying topics that used to be in the old mathematical tripods, and one of those topics is higher algebra, which was a topic that was prominent in first year mathematical courses back in the 1900s, right? In your first 4 years, or your 4 years in university, your first year would consist of higher algebra study, and progressions was an integral topic of that. I think it covered about 3 chapters worth of material. But what I would like to go through today is a basic introduction to sequences and series. Not too much though, because this is just going to lay the foundation for our main discussion, which is the 3 main progressions I'd like to talk about. Now, a lot of people might be thinking, I thought there are only 2 kinds of progressions. Well, 2 of them are the ones you probably already know, if you do know progressions, and that is the arithmetic progression and the geometric progression, right? Also known in our shorthand term as the AP and the GP. Now, these 2 I will be using to refer to as AP and GP from now on, just to make it easier. And then the last thing I would like to talk about is a kind of progression that is not really taught anymore in schools today, and that is the arithmetico-geometric progression, or the AGP. Now, this is a special kind of progression in that it actually fuses the 2. Right? There's actually another kind of progression called a harmonic progression, which we're not going to cover in this video, but if enough interest is there, I might make it, or if I want to. So let's start with talking about what sequences and series are. So a sequence in general terms is just a list of numbers that follow a specific pattern. So for example, if I take a look at the list of odd numbers, right, you'll see that they generally follow a specific pattern. Like it starts with 1 and then each subsequent term adds by 2. Now, of course, a lot of people might say, well, odd numbers in general, their pattern is that they're not divisible by 2. But in this case, the list of odd numbers is a sequence because they each follow a specific pattern, and each term has a sort of relationship with the previous one, right? And not all sequences have to do that. Like, for example, if I look at the sequence of all powers of 2, if I start with 2 power 0 as our first term, then you'll notice that the pattern here, right, and I'm going to write out all their respective numbers, the pattern here is that these numbers increase in terms of the power, right, of which 2 is raised to. So sequences usually follow a specific pattern, and this pattern is dictated by a general formula for what term in the sequence you want to obtain. So let's use some lingo first. This is usually known as the first term. Now, any element of a sequence in general is known as a term. Right? Any element in general is known as a term for the sequence, and the first term is called the first term. Now, for convention's sake, right, this is very important. For convention's sake, we will denote the first term as the first term and not the 0th term, because you may see some places denote the first term as the 0th term. We will not be using 0th term because in some cases it's useful, but in our context, it might be easier to just start with the first term because it is more intuitive to think of the first term as the first and not the 0th, right? So enough of that. Let's get into looking at the most important part of this section, which is looking at what exactly is the general term of a sequence, right? General term. Now, a general term of a sequence, in long story short, it's essentially just a formula which gives you any term you want out of a particular sequence that follows a specific pattern. So for example, for the term of all odd numbers, they generally follow a specific pattern that looks like this. It follows a sort of 2n plus 1 sort of format or formula where n here goes from 0, then to 1, then to 2, and so on. right? Because if we plug 0 in, we get 1. If we plug 1 in, we get 3. If we plug 2 in, we get 5, and so on. And this is essentially what we call the general term of the sequence. All right. Now, if we're going to talk about in general, we are going to need a symbol to denote what the nth term of a sequence is, right? Nth term in this case just means the term in position n in the sequence. Now, we are not going to keep writing the word nth term because I'm a bit lazy. So we're going to use some notation here. We usually denote it in either capital Tn or un. I'm going to use Tn here because Tn makes more sense because it is the nth term. Right? This n here is at the bottom, which we refer to as a subscript. Right? Just some terminology here, but subscript essentially usually refers to a numbering that's placed below a letter to denote some form of position. Right? Superscripting, which is the top here, is usually used for powers and for denoting several orders of magnitude. But this one usually is used to refer to position and ordering. Right? So we can say that the nth term, or the Tn of the sequence, is 2n plus 1, where n starts at 0. So n is at least 0, and of course n has to be an integer because we're not dealing with half term or like the pi term. That doesn't make sense to us. We're looking at integer terms here. All right. So to refer to our other example here, the powers of 2, here we say that the 2 power 0 here starts at 0. And I'm actually going to fix this one a bit, I just noticed, because if we say n is greater than or equal to 0, that would mean that we start with the 0th term, which doesn't really make sense. So we're going to change this to a minus and then change it to start from 1 instead. So therefore, we can say that the first term, right, is when n is equal to 1. Right? Because we want the n's here to match. We don't want here to refer to 0 and here to refer to 1 instead. We want both of them to refer to the same number. So therefore, let's say we plug in 1 here, T1, and we get 2 bracket 1 minus 1, which gives us 1, which is exactly correct. And you can check for yourself if you plug in subsequent values of n into here, you'll see that the second term will give us 3, third term will give us 5, and so on. All right? Now for this powers of 2 sequence, we can just simply notice that the pattern here is that it's going to increase, the power is going to increase by 1 each time. But what is the Tn in this case? Well, the nth term is, if we see, going to be 2 to the power of something. But that something is not exactly n because this is the first term, this is the second term, this is the third term, this is the fourth term. You notice that the number, the power here, is always 1 less than the actual term. So in general, we can say that the Tn for the sequence is going to be 2 to the n minus 1 because it's going to be 1 less than the actual term itself. And that's going to be the general formula or general term in this sequence. All right, so this is just a brief introduction to sequences. Let me briefly talk about what series are, because series are important for a certain aspect of progressions. Series are essentially just a sum of terms. So for example, 1 plus 3 plus 5 plus 7 plus 9 plus so on, all the way up to, let's say, 49. This is a series because it's a sum of terms, right? And the series can refer to a sum of any number of terms, and we can deal with finite and infinite series, right? Finite series means they stop at a certain term. Infinite series means they sum to an infinite number of terms. In similar fashion, I didn't mention here, but a finite sequence would stop at some point. So maybe this one stops at 49. This is finite. This one, on the other hand, if we say it goes on forever, this dot 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 means it goes on forever, then this would be an infinite sequence because it never ends. All right. In a similar fashion, if we said, look at this, for instance, and say 1 plus a half plus a quarter plus an eighth, and so on, we would say if this never ends, this is considered an infinite series, right? Because it's the sum of an infinite number of terms. All right. And this, in this case, this would be a finite series because it stops after a certain number of terms. You could also call it a sum, right? And obviously, the more intuitive way to say, oh, it's an infinite sum or an infinite finite sum, right? But series is the fancy word for it. All right, now that we are done with the prerequisites, let's get talking about arithmetic progressions first. So what are arithmetic progressions? Well, arithmetic progressions are essentially a kind of sequence where each subsequent term in the progression increases or decreases by a certain amount. So we say, or it follows a specific pattern. All right, so the pattern here is that let's take an example of an arithmetic sequence or an arithmetic progression. So if I remember, if I'm doing this correctly, yes. All right, so some of you may already be able to spot the pattern here, but if you notice, each term here increases by 3. All right, I'm not going to draw for all of them, but you notice all of them increase by 3. Now, this is an example of an arithmetic progression because arithmetic progressions have a constant increase or decrease with each subsequent term. And the terms don't have to be positive either. If let's say we had the term start at 1 and subtract by 2 each time, this would be -1, then -3, then -5, then -7, and boom, you have all the negative odd numbers starting at 1, which is not the negative odd number, but you find a way to construct every single negative odd number. All right, so let's talk about some notation for a sec for arithmetic progressions. So first off is the first term. Now we're not going to keep using the word first term, but we're going to use a certain letter to denote first term. Now we can use T1 because it reflects exactly what we would use for the nth term, which is perfectly fine. But I'm going to use another letter, which is another common letter, which is just to use A. All right, A in AP or GP terms usually means the first term. This works for GP as well, we'll see later. And this right here denotes the first term in the sequence. That's it. Next is going to be the nth term. Now, nth term, usually we just mentioned, is Tn. And the final thing, which we need to talk about, is what's known as the common difference. So common difference basically refers to this number right here. Right? So common difference refers to how much does each term increase or decrease by based on the previous term. Right? So obviously, because it's a difference, we're just going to denote small d. Right? So the small letter d will denote the common difference of a certain arithmetic progression. So for instance, if we took this progression right here, this 4, 7, 10 one, here our first term is 4, and our common difference is going to be 3. For this one, our first term is 1, and our common difference is actually -2 because each term decreases by 2, so it's a -2 common difference. All right? So every single time we talk about progressions, we want to talk about two specific things. One, how do we denote the nth term of that progression? And two, how do we denote the sum? We'll get to the nth term first, and then we'll get to the sum later. So nth term basically means we need to know how to find a general formula for any term in any arithmetic progression, no matter the first term or the common difference. So what we need to do is we need to generalize and think about a general arithmetic progression. So a general arithmetic progression would just be any progression that starts with some first term, so some a, and then increases by a d each time. This d can be positive or negative. Remember, we're just using plus because it's convention to add rather than subtract, because subtracting is just adding a negative, right? So the next term after a plus d would be adding a d to this, which would be a plus 2d, then adding again a plus 3d, a plus 4d, and so on, right? So if we notice here, this progression, we can attach the t1s and t2s and so on to each term. We can assign them like this, right? And doing this, we find that each term, there's some relationship between the term number here, the subscript, and the coefficient of d here. Because if we notice, here there's no d, here there's 1d, and here there's 2, 3, and 4, and so on. So we notice that this number is always 1 less than the actual tn, or the 1 less than the actual n. So if we were to sort of do pattern spotting, basically, and notice that this will work for every subsequent term. We're just going to keep adding d, 1d each time. All right, we're going to keep adding an extra d each time, and notice that it's just going to be 1 less than the n. That means we're going to always add an n minus 1 times d to the n, and then a remains constant. Right? And that makes sense because a is always present in every term, right? Because you got to start somewhere, you're going to start with the first term. Now, n minus 1 is because we just said this coefficient is always 1 less than the actual n at the bottom of the t. So we're going to use n minus 1 to denote that the nth term is going to have n minus 1 d's added onto our initial a. And this is why the first term has no d's, because the first term is just a. So this term would naturally be 0, which is why if we plug 1 in, this whole term becomes 0. Right? So this is in fact the general formula for the nth term in an arithmetic progression. Right? This is for arithmetic progressions. Okay. Now the second thing that we talk about in an arithmetic progression is the sum. More specifically, we call sum of first n terms. Right? There are more specifically more difficult ones that I may make a video on, but for now, this video will focus on the basics of progressions, not the complicated stuff. All right? So we're going to talk about what's the sum of first n terms mean. Well, what it means is that if I say I want the sum of the first 10 terms of the arithmetic progression, right? What I would mean is 10 would mean that I would want to sum from t1 to t10. So I would want to say t1 plus t2 plus t3 and so on all the way until t10. Right? This is what it means to have the sum of the first 10 terms. Right? You take the first 10 terms and you just sum them together. So in general, what we want is the sum of the first n terms. Now we're going to give some notation again because I'm not going to write this phrase over and over again. So we're going to use capital S of n to denote sum of the first n terms. All right. So how do we figure out a formula for this? Well, we're going to need to do some experimenting here. So let's come back to our general arithmetic progression again. But this time, we're actually going to put it to a stop somewhere, because this is a finite sum after all. We're talking about the sum of the first n terms. And by the way, let's talk about the more obvious case. If this sequence were to go on forever, there would be no n, obviously. So there is no such thing as an infinite sum of progressions. You can't say the sum of all the terms in this progression, because the sum would, what we would say, diverge, meaning that the number is so big or so small that it doesn't lead anywhere. Because if you say 1, 2, 3, all the natural numbers, these are all perfectly fine, and this is a arithmetic progression because the first term is 1, and each 1 increases by 1, so we have a common difference of 1. But if you were to sum all the possible natural numbers together, in common sense, that goes to infinity. So there's no sum there. So we generally don't think about the sum of all the terms in an arithmetic progression because it leads to infinity or negative infinity. Okay, so we're going to stop it at the nth term, which we just mentioned up here. Right? So what we're going to look at here is an observation made by one of the most famous mathematicians of all time, Gauss, because Gauss is actually the one that found out this pattern, which led to the discovery of the sum of a number of terms in arithmetic progression. So to illustrate that, let's look at an example. Let's take a look at what happens when you try to sum the first 10 odd numbers. Right? So if we go all the way to 19, which is the 10th odd number, we want to be able to, all right, let me write out every single of those 10 odd numbers because this one is important to illustrate. Okay, so what we want is an easy way, rather than just adding these numbers up one by one. We want to find the sum of all 10 of these odd numbers, right? This is the sum of the first 10. So essentially what we want is S of 10 of the sequence. So what Gauss noticed is, let's take the first term and the last term and then add it up. What do we get? Well, we get 20. All right? Not really anything interesting. I mean, that's obvious. But what Gauss did was say, okay, let's move this forward by 1 and move this backwards by 1. And let's sum those two terms. Let's take 3 plus 17. You notice, oh, we get 20. Let's do it again. Move this forward by 1, move this backward by 1. We get 5 plus 15, which gives us 20. Do it again. 7 plus 13, that's 20. And then again, 9 plus 11, we get 20. If you notice, there's nothing in the middle here now. So we've essentially added up all the terms now. So what he found, and what you may be able to notice if you're smart enough, is if you add all these terms together, you would essentially be able to get the sum of all those terms. And then all the way up to 19. right? And that would be equal to the sum of these 5 20s, which would be equal to 100 because it's 5 20s. So what he noticed is that if you repeat this process, right, that seems to indicate that the sum of any arithmetic progression can be obtained simply by doing this over and over again, which is we keep taking the first and last, and then we keep shifting, and then we sum them, and then we take that sum and multiply by a certain number of times. Now, the important thing is that number of times. How many times do we multiply that sum by? Well, if we notice, because this has an even number of terms, this one's 10 terms, we will be able to group this sequence into 5 distinct pairings, right? Because it is an even number of terms, we will be able to pair up the first and last term, like these first last term pairings, by shifting forward and just shifting backward. We'll be able to pair up each term front with a term back to get a certain number, a fixed number of pairings, right? And how many pairings can we make? Well, if there are n terms, if there are 10 terms here actually, we just have to divide by 2 and we get 5. So we get 5 pairings. So in general, right? So we're talking about even terms here, right? If n is even, right? So if we have an even number of terms we're trying to sum, we just have to take S of n, right, is going to be equal to n over 2, which is essentially the number of pairings that we make, multiplied by that sum. And if we notice, that sum remains constant. And we can actually prove that that's constant. Why? Because t1 plus tn is equal to a plus n minus 1 d, or 2a plus n minus 1 d, right? Now if we take t2 and add it to tn minus 1, we get a plus d plus a plus n minus 2d, right? And if you sum this up, you actually find that this also equals 2a plus n minus 1d. So in fact, in general, if we see t of some k plus t of n minus, well, this number is going to be 1 less than k. So it's going to be k minus 1, right? Which is in fact equal to tk plus tn minus k plus 1. All right, this is going to be equal to a plus k minus 1 d plus a plus n minus k plus 1 d. And you can simplify the algebra here yourself to find that this equals 2a plus n minus 1d. So in fact, if we just keep moving back front here, moving here front and moving here back, we will keep getting the same sum over and over again. And because we know how many pairs are going to be made, we just have to take that sum, right, which is this number, which is this term right here, and then multiply by the number of times or the number of pairings we make. So that sum, we can either write t1 plus tn, because that is one way, because it is the t1 plus tn, or in general, we can write it as n over 2 times whatever represents that term, which is 2a plus n minus 1d. So this is actually the sum of n terms in an arithmetic progression if n is even. Right? Now, this may be a bit anticlimactic because it's like, oh, we only dealt with when n is even. So let's look at the alternative. What if n is odd? So if n is odd in this case, if n is odd, then we would have leftover. Actually, 1 leftover exactly. Because if n is odd, then the n over 2 is going to give us some odd number. So we're actually going to get n minus 1 over 2 pairings and then 1 leftover term. So S of n is actually going to be equal to the sum of those n minus 1 pairings. And by the way, this inside term doesn't change because we are still adding the first term and the last term. So it's still t1 plus tn. So the term here, the sum here actually doesn't change, right? Because even if there's a leftover element from the odd pairings, every other pairing is still going to produce the same sum. We still have n minus 1 over 2 is an even number, because n is odd. So n minus 1 over 2 is going to give us a specific number of pairings. So if n is odd, we're just going to have to take that and then plus that leftover term, right? Because every other term, except the leftover one, has been paired. So we just have to add it with whatever that one is. Now, what is exactly that term? Well, that term is going to be the middle term, because if we notice the pattern here, when there's an even number of terms, when we approach the middle, we notice that there's nothing in the direct center. But for example, let's say we took the first 7 odd numbers. So 1, 3, 5, 7, 9, 11, 13. If we were to do this moving front and then moving back maneuver, we notice that they both approach the same term. Right? This one is the only one, if you can see, that has no pairing, because each one of these can be paired except this one. They both approach this one center term. So the center term is actually the middle term. So what is the middle term? Well, it's basically just you could say the median of this whole sequence, right? In statistics terms, we say this is the median of this whole sequence. So it's actually the t n plus 1 over 2 term, because it's the middle term, right? If there's 7, we're looking for the 4th term, because that's when that's basically when the arrows all point the same spot. Or if you want to make it easy for yourself, just take n minus 1 over 2, because that's how many pairings there are. Take n minus 1 over 2. That's how many pairings there are. And then add 1 to it. Why? Because the n minus 1 over 2 will refer to how many pairings there are. Well, the last term in the front that gets paired is this one, right? And the term number of this will exactly correspond to how many pairings there are, because the next term after it is the center one, so there's no pairing. So the one with no pairing is the leftover one, which is the one after the n minus 1 over 2 term. Right? This one right here actually is the n minus 1 over 2 term, right? Because this is the last term in the front that has a pairing, right? You could also look at it from the back, but it's much easier to see it as, if we count from the front, there will be one last term that has a pairing, and then the term after it has no pairing, which is the term we're looking for, which is n minus 1 over 2 plus 1. And this one will simplify to n plus 1 over 2. And that's why we choose to replace this by n plus 1 over 2. Okay, so we're going to have to do a bit of algebra here. So this is actually going to be, we're going to simplify out this one first. Actually, no. Let's expand out that n plus 1 over 2 term first, so we can see what ends up coming out of it. So this gives us a plus n plus 1 over 2 minus 1 times d, which if we simplify, n minus 1 over 2 times 2a plus n minus 1d plus a plus, this is going to be n minus 1 over 2 times d. All right, so if we simplify this with some algebra, we will see that this is a times n minus 1, and then we're going to add another a here, so it's actually plus 1, right? Because we have, if we expand this out, expand this, we will notice that the factors of 2 cancel out, so we have a times n minus 1 left, and then we're going to add an extra a here, so it becomes plus 1. And then the d will have a coefficient of, well, that's going to be n minus 1 squared, because we multiply n minus 1 twice, over 2. But then we're going to add this term, which is an n minus 1 over 2 term, right? So this is actually the coefficient of a and the coefficient of d. Now this goes to a, and then this becomes n squared. This is going to be minus 2n plus n, which is minus n, then plus 1 minus 1. So we have n squared minus n over 2 times d. Now, we can actually sort of simplify this out a bit, right? And the way we're going to simplify this out is we're going to add, or should I say, we're going to factor n over 2 out. Why? You'll see why. If we factor out n over 2, then this one, and n is factored out, but we factor out a half. So we actually have to put a 2 here, because if we expand this in, we get back our original term. Now this one is fine, because if we factor our 1/2 out, we get n squared minus n. We factor another n out, we are left with n minus 1. Now this, if we see here, this is for the case when n is odd. Right? Because we said that we had to have an even number of pairings added with that leftover term. But this is exactly the same as the even term. So coincidentally, all right, so in conclusion, essentially, for any arithmetic progression, the sum of the first n terms is going to be n over 2 times 2a plus n minus 1d, or n over 2 times the first term plus our nth term. Right? And this is true for any arithmetic progression with any first term in common difference. And that's the amazing thing that Gauss actually discovered. Right? So this is actually just part 1 of the 2-part series. I'm going to have to stop here for now. Next part, we're going to be talking about our remaining 2 sections, which is the geometric progression and the arithmetical geometric progression, which will be in part 2 of this video. So that's it for me. Stay tuned for part 2, and I'll see you guys next time.